Okay, so imagine you're at the beach, you know, just looking out at the ocean.
Ah, nice.
Waves are crashing and the tide's going in and out. And then you look up and there are billions of stars.
Yeah.
It's beautiful, right?
Mhm.
But it's also kind of powerful in a way.
Absolutely.
And it's all controlled by these four forces.
It is, yeah.
Welcome to Cosmos in a Pod, the space and astronomy series. Please like, comment, share, and subscribe.
We appreciate it.
So these forces, they're kind of like the rules of the universe. They
Yeah.
tell everything how to behave.
That's right. Everything from the tiniest particles to the largest galaxies.
So are we ready to dive in?
Let's do it.
Okay. So I think the best place to start is with gravity.
Okay, yeah, the most familiar one.
Right. Everyone knows about gravity.
Right, it's what keeps our feet on the ground.
Exactly. And it makes the planets go around the sun.
Mm-hmm. Holds the moon in orbit around the Earth.
But I've always wondered, if gravity is so important, why is it called the weakest force?
That's a good question. It seems counterintuitive, right?
It does.
But even though it's weak compared to the other forces, it has a couple of advantages.
Like what?
First, it has infinite range, it never gives up. And second, it's always attractive, never repulsive.
So even if it's weak at like the atomic level,
Right.
when you get enough matter together, gravity starts to win.
Exactly. Like, think of it like a snowball rolling down a hill. It just keeps getting bigger and bigger.
I get it.
And that's how gravity shapes, like, galaxies and the entire universe.
Makes sense. But then Einstein came along and said, hold on a second,
Yeah, he changed everything.
with his theory of relativity.
Mm-hmm. He said gravity isn't a force at all. It's like a curvature in space-time.
Whoa, okay, so explain that one to me.
So imagine a bowling ball on a stretched-out sheet.
Okay,
The ball makes a dip, right? And anything rolling nearby will fall towards it.
okay, I can picture that.
So it's not that objects are being pulled together. They're just following the curves in space-time.
Wow, my mind is kind of blown.
It is pretty wild.
But there's still one thing missing, isn't there?
You're talking about the graviton.
Yeah, the graviton.
You see, we have this model of the universe, the standard model, and it explains all the other forces with these force-carrying particles.
Right.
But gravity doesn't quite fit in yet.
So the standard model is like a blueprint of the universe, but it's missing a piece.
In a way, yeah. And that missing piece is the graviton.
So if we find it, that would mean...
It would mean we could finally unify gravity with quantum mechanics.
And that'll be huge, right?
Absolutely massive. It would be a step towards a theory of everything.
A theory that explains everything. That'd be pretty cool.
It would revolutionize physics. Imagine understanding the universe at its most fundamental level.
Wow. So we've talked about the force that shapes the universe. Now let's go smaller,
Let's go.
like way smaller, to the heart of the atom.
Ah, the strong nuclear force.
Yeah, the strong force. What's that all about?
So, if gravity is the architect of the universe, then the strong force is the builder of matter. It holds the nucleus of an atom together.
The nucleus, that's where the protons and neutrons are.
Exactly. But here's the thing. Protons have a positive charge, so they should repel each other.
Right, like charges repel, opposites attract.
Right. But at these tiny scales, the strong force is much stronger than the electromagnetic force.
So even though they want to push apart, something is holding them together.
Yes, the strong force. It acts like a glue binding the protons and neutrons together.
And the glue is...
Gluons.
Okay, gluons, got it. So how strong are we talking?
Imagine trying to pull apart two incredibly strong magnets that are stuck together.
Okay, that's pretty strong.
It's so strong that a teaspoonful of neutron star material would weigh billions of tons on Earth.
Billions of tons in a teaspoon.
Yep, because it's packed so densely together by the strong force.
But if it's so strong, why doesn't it pull everything in the universe together? Why doesn't it beat gravity?
That's because, unlike gravity, the strong force has a very limited range. It only works inside the nucleus.
Ah, so it's like a super strong, short-range force.
Exactly. And gravity is a weak, long-range force. They balance each other out.
I see. But wait, there's another nuclear force, right? The weak force.
You're right. We can't forget about that one. It might not sound as impressive, but it plays some critical roles.
Like what?
It's responsible for radioactive decay,
Okay.
and it helps transform elements. It's actually what powers the sun.
So the strong force holds the nucleus together, and the weak force changes the elements.
Exactly. It's like the alchemist of the universe, constantly transforming matter at its core.
Wow, that's pretty amazing.
It is. The weak force is constantly at work, shaping the universe in subtle but profound ways.
Okay, so we've got gravity, The strong force, the weak force. What's next?
Well, the next one is the force that's probably most familiar to us in our everyday lives.
You mean?
Electromagnetism.
Electromagnetism, the force that literally lights up our world.
Yeah, it's responsible for electricity, magnetism, light, pretty much everything we use in our technology.
And the beautiful colors we see.
That too. And it's all based on one simple principle. Opposite charges attract and charges repel.
So the same force that makes a static shock when you rub your feet on the carpet
Yes.
is also behind those amazing northern lights.
Exactly. It's all thanks to the photon, the force carrier for electromagnetism. It zips around at the speed of light, connecting charged particles.
Wow, it's incredible how one force can do so much.
Yeah.
But you mentioned the Standard Model earlier.
Right.
Where does electromagnetism fit into that?
That's a great question. It turns out that electromagnetism and the weak force are actually two sides of the same coin.
Really? They seem so different.
I know, but physicists have unified them into a single theory called the electroweak theory.
So we've gone from 4 fundamental forces down to 3. Gravity, the strong force, and this electroweak force.
Exactly.
It makes you wonder, could we go even further? Could we unify all the forces?
That's the dream, isn't it? To find a single theory that explains everything. A theory of everything.
That would be amazing.
It would be a revolution in our understanding of the universe. Imagine the possibilities.
It's mind-boggling to think about. So what would a unified theory tell us about reality?
It would suggest that everything is interconnected at the most fundamental level, that there's a deep underlying unity beneath all the apparent diversity.
Wow, that's deep. But this quest for unification, it's not just about satisfying our curiosity, right?
No, there are practical implications too. Imagine harnessing the power of gravity for space travel.
Or creating new materials by manipulating the strong force.
Exactly. A theory of everything could revolutionize technology and our understanding of the cosmos.
It sounds like science fiction.
Yeah.
But the more we learn about the universe, the more we realize that anything is possible.
That's the beauty of science. It's always pushing the boundaries of what we thought was possible.
So we've traveled from the force that shapes galaxies to the forces that govern the heart of matter. And it seems like with every answer, we uncover more questions.
That's the nature of exploration. It's a journey without end, always pushing us to learn more.
And as we delve deeper into these fundamental forces, we gain a greater appreciation for the complexity and the beauty of the universe.
Absolutely. It's a reminder of how much we still have to learn and how much there's left to discover. It really is. And those transformations, they're happening everywhere, right?
Yeah, I mean, even inside us, in our bodies.
That's right. Like the weak force controls the decay of radioactive isotopes that are naturally in our bodies.
So even the weak force, it's important for life.
Definitely. It's a subtle force, but it's essential.
It's amazing how these tiny forces can have such a huge impact.
It is.
I mean, we've talked about gravity, strong force, weak force.
You're right.
But what about the force we see every day?
You're talking about electromagnetism.
Yeah,
The
electromagnetism.
force that powers our world.
Exactly. Our lights, our phones, everything.
Yeah, electricity, magnetism, light. It's all electromagnetism.
It's like the multitasker of forces.
It really is. And it all boils down to the interaction between charged particles.
So opposites attract, likes repel.
Exactly. That's the basic principle. And it governs everything from lightning to, well, a gentle breeze.
Wait, so the same force that gives you a static shock
Yes.
causes the northern lights.
That's right. All thanks to the photon, the force carrier for electromagnetism.
The photon. Zipping around at the speed of light.
Connecting charged particles.
It's crazy how one force can create such amazing things.
It is.
But hold on, we were talking about the Standard Model earlier.
Yes.
How does electromagnetism fit in with that?
Well, this is where things get really interesting.
Okay, tell me more.
It turns out that electromagnetism and the weak force, they're actually connected.
No way, really. They seem so different.
I know, but physicists figured out that they're actually two aspects of the same force.
Wow, so like two sides of the same coin.
Exactly. And this discovery led to the electroweak theory.
So now we're down to just 3 forces. Gravity, the strong force, and this electroweak force.
That's right.
I can't help but think, could we go even further? Could all the forces be unified?
That's the ultimate goal for many physicists.
The theory of everything, huh?
Exactly. A single theory that explains everything in the universe.
That would be groundbreaking. What would that mean for our understanding of, well, everything?
It would suggest that everything is connected at the most fundamental level. a deep unity beneath all the diversity we see.
It's almost a philosophical idea.
It is, but it has real implications for science and technology as well.
I mean, imagine what we could do if we could control these forces.
Exactly. We could revolutionize space travel, develop new materials. The possibilities are endless.
It sounds like something out of a science fiction movie.
Maybe, but who knows what the future holds? The more we learn, the more we realize anything is possible.
Okay, so we've covered gravity, the strong force, the weak force, the electroweak force.
There's a journey.
It is. But it seems like the deeper we go, the more questions we have.
That's the beauty of it. It's a never-ending exploration.
It's humbling, you know.
It is, but it's also incredibly exciting. There's so much more to learn.
Speaking of learning more, we've been talking about forces in atoms and galaxies.
Right.
But there are some places where gravity is the main player.
Oh, you mean black holes?
Yeah, black holes. Those places where gravity is so strong, nothing can escape.
They're fascinating, aren't they? Regions of space-time where the laws of physics are pushed to their limit.
Exactly. It's like gravity wins there.
It does. Black holes are like cosmic laboratories where we can test our theories about gravity.
So even though they're dark, they can teach us about the universe.
Exactly. By observing how matter behaves around black holes, we can learn a lot about gravity and how it interacts with the other forces.
It's incredible that we can even study them. We're actually seeing images of black holes now.
It's amazing, isn't it? We're seeing these objects that were once just theoretical.
And who knows what else is out there, waiting to be discovered.
The universe is full of surprises, that's for sure. Every new discovery pushes the boundaries of our knowledge even further.
It's a reminder of how vast and mysterious the universe truly is.
It is. And it's a call to keep exploring and keep asking questions.
Yeah, it's like peeling an onion. Every layer has another layer.
And sometimes those layers make you cry a little.
That's a good one. But speaking of layers, we've talked about forces in atoms, in galaxies. But there are places where gravity is like the star of the show.
Ah, you're talking about black holes.
Yeah, black holes. Those places where gravity is so strong that nothing, not even light, can get out.
Right, they're like cosmic vacuum cleaners,
Yeah.
sucking up everything around them.
Exactly. They really test our understanding of the universe.
They do. They're like a proving ground for our theories about gravity.
So even though we can't see them directly, they can teach us a lot.
Exactly. We can study how matter behaves around them, and that gives us clues about how gravity works in extreme conditions.
And now we can even take pictures of them, like that supermassive black hole at the center of our galaxy.
I know, it's amazing. It's like we're peeking into the heart of a monster.
It makes you wonder, what else is out there? What other crazy things haven't we discovered yet?
The universe is full of surprises, that's for sure. There's always something new to find.
So as we wrap up our deep dive into the 4 fundamental forces, I'm feeling a little overwhelmed, to be honest.
Yeah, it's a lot to take in, but it's also pretty inspiring, isn't it?
It is. I mean, we've learned so much, but it's clear that we've only scratched the surface.
That's the beauty of science. There's always more to learn, always another question to ask.
It's like we've been given a glimpse behind the curtain,
Yeah.
you know, a peek at the machinery that makes the universe tick.
Exactly. And even though we don't understand everything yet, that glimpse is enough to make you appreciate the wonder of it all.
It really is. So here's a final thought for everyone listening. We've talked about how these forces shape everything around us.
Yep.
But if they were all unified in the early universe, what does that tell us about the nature of reality? Are we all connected in some fundamental way?
Those are big questions, questions that scientists and philosophers have been wrestling with for centuries.
And maybe someday we'll have the answers.
Maybe. But until then, the mystery remains. And that's part of what makes the universe so fascinating.
It definitely does. Well, that's about all the time we have for today.
Time flies when you're talking about fundamental forces.
It really does. We hope you enjoyed this deep dive into the 4 forces that shape our universe. Be sure to follow Cosmos in a Pod and subscribe to our YouTube channel for more fascinating explorations into the cosmos. Until next time, keep looking up.